Okay, welcome everybody. Good to see so many people. I really appreciate you coming to the behind-the-scenes look at generative AI infrastructure here at Amazon. I'm Gadi Hoot. I run Director of Product and Business Development at Annapurna Labs. With me will join us today our customers, Mr. Naveen Rao, VP of Gen AI at Databricks, and Mr. Pete Werner, the Head of AI at Leonardo AI. Together, we'll tell the story of how Gen AI infrastructure works at AWS. We have a pretty packed agenda. In order to tell the story, I thought we'll start with some history of how we got started at Annapurna Labs, key steps and decisions we took along the way, and then we'll go through the hardware progression, software progression, latest benchmarks and numbers, and then we'll hear from our customers, and we'll do a quick summary at the end and some glimpse to the future. So let's get started. Annapurna Labs is the team within AWS that builds all the purposely built chips. You're probably familiar with the Nitro product line, with Graviton, and of course, Inferential and Training will be the focus of today. Since the beginning, we knew that even that we are building silicon products and hardware-centric products, our customers will be all software developers. And it's a key distinction because our silicon architects not only need to know the latest technology in silicon, they actually have intimate understanding of the software layers and ecosystem that these chips need to work with. And this means that we take very specific decisions to ensure that the hardware fits what our customers need from one hand, and of course fits what how AWS deploys at scale in the data centers. Building the wrong piece of silicon is a very, very expensive mistake. Not only capital expenditure that has to be restarted, but also in time. If there is a bug in silicon that cannot be worked around, it will take 9 months, up to 9 months to fix the silicon. So it's super important to make the right decisions. Let's see how we do this. Since we founded Annapurna back in 2011, any product that we built was based on 3 key tenets. Portability and reusability is a very clear concept in the software world. When you write code, you want to be able to reuse the code, you want to be able to deploy it in different locations. But similar concept we took into the silicon space. We are only hard coding pieces of silicon if there is a well-defined standard, think Ethernet or compression or encryption. And of course, anything that is data crunching, that's where the acceleration is coming from. Anything else will be software programmable, so we have a lot of flexibility to address the future needs of customers. All the products have to be easy to use. If it's hard to use a new piece of technology, it's pretty simple. Not many folks will want to walk the journey. And the last one is kind of obvious. Cost and cost to performance. If the products don't provide value to customers, then again, the adoption will be negligible. So let's go back to 2017. Back then, we started to see key businesses in Amazon, like Amazon Go, like Prime Air, like Alexa, and also AWS services like Rekognition, Lex, starting to use deep learning in a meaningful way. At the same time, we started hearing from customers that the cost of running these models and the performance has to improve. Today, it's way more obvious than it used to be back in 2017 with Gen AI, but even back then, we noticed that, and we took a bet that the models and the compute intensity of these models will continue to grow. So we wrote a business case. In Amazon, it's called the 6-pager, and we basically outlined why we think back then in 2017 is the right time to start building machine learning chips. And we landed on a few main opportunities to help customers. The first one is optimization. We knew from previous product lines like Nitro that we can get higher utilization if we build the chips purposely for machine learning. Lower cost if we design and manufacture in-house and have full control of the hardware and software stack, that will enable us to increase utilization and lower the cost to customers. Performance, we knew we'll have to innovate on the software stack and of course in hardware to make sure that we can meet the performance our customer needs. And integration, we were in a unique point in time where Nitro was already a mature product line with multiple generations already deployed, and we had a lot of Lego pieces that we could reuse in order to build the machine learning servers. On the model landscape, back in 2017, computer vision was very common. This is ResNet. And then there were other models for like LSTMs for NLP, natural language understanding, and some vector-based representations like Word2Vec. What you can appreciate is that all these model architectures are fairly different, but they had commonalities. We noticed that all of them are neural network-based, so that means massive linear algebra computation, so it's a good opportunity to accelerate. And 95% of these operations are matrix operations. Mid-2017 came the famous paper, Attention is All You Need, but the first model that was popular based on that paper came out in 2019, that's BERT. In 2019, we already had the chips at hand. So it's super important that the chip that we designed will be able to address all of these different architectures. So, when we design the chips, we can use two methods, right? We can have the crystal ball method, where we try to predict what will happen 2 years down the line, because it takes 2 years to design, manufacture, and test a piece of silicon and then deploy it in the data center. Or we can use inversion. Inversion basically encourages us to inspect the problem, not head on, but actually from the opposite direction. And our problem was we didn't know what will be the popular models in 2 years, but we could guess what's not going to change. So that took us back to our tenants. Customers will always want more performance, they will want better cost structure, and a service that is easy to use. And for us, as the design team, we wanted hardware that we can reuse generation over generation and kind of grow on the capital that we have. So let's see how we did this. It's kind of hard to show in slides how we design chips, because basically you'll see pictures of folks coding on computers. But I can tell you that we had to build a new team. And we did that organically. It basically was a startup within Annapurna Labs, which is a startup within AWS, which is a conglomerate of startups. Back then, we had only less than 10 chip engineers, no compiler or application engineers, and very little previous ML experience. Don't get alarmed, this picture is not a data center in AWS, it was generated by Stable Diffusion on Inferentia. But, so let's go and talk about hardware a bit. This is Eran, he heads our hardware team, and he's now carrying the first Inferentia chip. So after we did all the work of the design and simulation and manufacturing, everything comes back in a box. And there are a few chips in that box, and this is what Eran is carrying back into the office. And the folks started working on the servers. You can see it's really a startup mode. These are the first Inferentia servers. These are Inf1s. And Jake and Rohit from our hardware and software team are hand assembling them in the lab. Well, I don't see a lab here. Again, it's a startup mode. They had to do it on the floor. We didn't have tables yet. If you can look at the back, you will see the lab is getting built alongside the servers. So really a startup mode. But then we get to scale. In order to build these servers, you need huge manufacturing facilities that build the racks, do the cabling in the racks, run the testing, and of course assemble the servers. On the right-hand side, you see the Inf1 servers. It's a 4U server. What you see here is the power delivery, the fans to cool, and then of course the cards that have the chips on them. We were able to pack 16 chips inside the 4U server, and you can see it's kind of an origami game on how to lay out the cards. But the result was pretty amazing, because after we finished manufacturing, we actually had the first Inf1 server running inside the data center. So that's the picture that you see here. You can see the server is pretty clean, but you know it's complex from the inside because you've just seen it, the insides of it. But more importantly, we had to deploy these things at scale. So today, we have Inf1 servers in 23 global regions in AWS. Each region is many data centers, known also as AZs. and we have thousands of these racks deployed. In one word, I think we can summarize it: massive scale. But this was only the beginning. Looking at these inference racks, like I said, you can see they're pretty clean. There is top of rack, which is accidentally in the middle of the rack. Actually, not accidentally. It's easier to do cabling if it comes from the middle. And now let's look at the TRN1N servers looks like, our training machines. I hope you can appreciate that there is a lot more going on here. So don't worry, let's break it down. So this is TRN1, just a bunch of Trainium box. In the back end, like Inf1, you see power delivery and fans. In the middle, this is where the Trainium chips reside. And I have here with me one of them. You can just appreciate, I hope you can appreciate the size. And we have 8 of those inside the box. It's pretty heavy, so I'll put it down. And this is the main section, of course. At the front, we have Neuron Link. This is the technology that allows us to interconnect all the chips in a 3D hypercube, 2D torus configuration. And basically what this ensures is that there is a maximum of 2 hops between each chip. And that gives, of course, minimum latency and it's a high performance, high bandwidth interface. So going back to the racks, a single TRN1 server is actually 3 separate boxes. There is a head node at the top, and then there are 2 of the boxes we just reviewed, giving a total capacity of 16 Trainiums that folks use to run training workloads. And of course, each rack has multiple servers in it. Let's look at Inferentia, Inf2. So after we launched Inferentia 1, we launched Inferentia 2. The Inf2 servers provide 3x the performance as compared to Inf1 and enable LLM and Stable Diffusion Gen AI workloads. Let's look at the server itself. The back is very similar, power delivery, fans. In the middle, we have 12 Inferentia 2 cards, and those are here. This is how it looks without the cover. You can appreciate, at least from the size, there is quite a difference. The reason is, for inference workloads, we can lower down the compute because LLM inference is mostly memory bound, not compute bound. So the more memory bandwidth you have, the better the performance will be. And Inf2 is the only server that is optimized for inference in the cloud that enables interconnectivity between all of those 12 chips to allow for LLM deployments at scale. At the front, this is a single server. At the front is an x86 compute. And you can see the 2 Nitro cards, one for storage connectivity and one for networking connectivity. So we talked about the servers. Let's take a quick look on the chips themselves. On the right-hand side is Inferentia. On the left side is Trainium. Compared to Inferentia, Trainium has 5x the number of transistors. So it's a way more complex chip. We also added HBM, high bandwidth memory, that allows to unleash the performance of the compute. The chips are, like I said, 3x the compute. And you can also appreciate it's more advanced packaging technology to fit all of those pieces of silicon into one package. Let's dive into the chip itself. You guys are, I don't know if you are ready for this complexity, but don't worry, I'll guide you through it. So the main thing, if you guys remember, I mentioned linear algebra. The main engines are the neuron cores. We have 2 of them in each Trainium. Excuse me. Yeah, we have 2 of them in each Trainium. The main component is the tensor engine. That's where all the compute happens. There's also a large SRAM on-chip memory that minimizes memory movement so we can maximize the compute. And there are other engines for the 5% of the work of the operations I mentioned earlier to do things like scalar operations, vector operations. And also, there are 16 general purpose SIMD cores. Those are important because that's the programmable part I was talking in the beginning. If there is something that cannot be expressed or optimally run on the compute cores that we designed, you can write C++ code and just run it on the SIMD cores with a very high bandwidth to the memory. On the side is the HBM memory that we just seen on the chip itself. And in order to enable the connectivity across multiple chips, we have 4 neuron links on each chip, and of course, a set of DMAs, and importantly, a separate collective compute engine. Collective compute are the operations that allow to synchronize between multiple chips while you do training or inference. And for us, we decided to put a dedicated engine for that because it allows us to overlap compute and communication, and by that accelerate the training or the inference workload. So now that you are experts in the chip technology and how the servers look like, I hope you can appreciate how we build a server. We basically have 16 of those Trainium chips inside this server, giving memory capacity, high bandwidth memory capacity of 512 gigabytes, and a peak memory bandwidth of 13.1 terabytes per second. Just to pause for a second, an SSD is roughly 2 terabytes. 13 terabytes is 6.5 SSDs being read every second. Just to explain how much memory bandwidth exists in this box. And similarly with Inferentia 2, we put 12 of the Inferentia 2 chips. What we have done is, in terms of the silicon architecture, you can see it's fairly similar. The main difference on the chip itself is less neuron links, because we don't need a lot of connectivity for inference. So we were able to cost reduce the chips a bit and then provide the value to customers in terms of cost to inference. And how it looks in terms of numbers. This is Llama 2 training done on TRN1 compared to the latest generation comparable EC2 instances. In one word, you get up to, you basically pay 50% less, roughly 50% less to train on Trainium versus the alternative solutions on EC2. And this is true for 7 billion, 13 billion, and 70 billion Llama 2 models. The way we measure it, by the way, is effective flops per dollar, which is the same to say as cost to train. Similar picture on the inference side. This is comparing Inf2 to the latest alternative inference instance in EC2. And you can see almost 5x lower cost to deploy Llama 2 across 7 billion, 13 billion, 70 billion with Inferentia 2. So huge benefits to customers who decide to use those accelerators. And we have quite a few of those customers. Of course, I'm hoping everybody heard Dario in the keynote from Anthropic, who are developing the next generation models on top of Trainium and Inferentia. Adobe, who are adopting Inf2 to their Firefly generative AI image service. Stability AI, who are seeing 30% lower cost to train their LLM models in multiple languages, and 60% lower cost per image when they use SDXL. And also worldwide, we have customers from Japan, like Stockmark, who has trained a 13 billion Llama model to speak Japanese. So Llama now can say arigato, and they did that in less than a month on top of Trainium, and of course with significant savings like you've seen. And also Rico is deploying Llama-like models in Japanese and train them on Trainium. By the way, the Stockmark model is available on Hugging Face, which is pretty cool to see how the customer ecosystem is also starting to contribute back models that were trained on Trainium. And of course, we have Databricks and Leonardo that you will hear about from today. Let's talk a bit about the software. So our software SDK is called Neuron. We'll show you a bit how to use Neuron, but we actually want Neuron to be as thin as possible of a layer and leverage as much as possible open source models, because open source code and frameworks, because that's what all of you are used to do with alternative infrastructure. So we always take the approach of a plugin. We have a plugin to PyTorch, a plugin to TensorFlow, and we are working on the JAX that is coming out soon. And also easy to use frameworks like Hugging Face and Ray. Of course, SageMaker, Jumpstart, all of those are available for training in Inferentia. And it literally takes a few lines of code. We'll take a look at that next. Let's focus on Hugging Face. Hugging Face is the most popular model repository in the world. Millions of models, millions of downloads. And they have been working on a package called Optimum Neuron. Optimum Neuron is essentially implementing the transformer technology to fit optimally and performantly into Inferentia and Trainium. And what that allows is a very large breadth of models that can work on Trainium and Inferentia. Happy to say that the latest is 93 out of the top 100 models in Hugging Face repo are performant on Trainium and Inferentia. Amazing partnership with Hugging Face, and this will just continue to improve from here. We'll get back to Hugging Face in a second, but before that, I want to talk about our compiler. The compiler is the main piece of technology that our team has developed, and it allows to take Python models and lower down to machine language performantly that the chip can run. Well, let's do a quick crash course in compilers. There are 4 stages. The first one is actually hardware agnostic. These are just generic graph optimizations that we are doing to optimize to minimize the amount of compute we can as much as possible. So those are operations like operator fusion or common sub-expression elimination, meaning if there are pieces of code that generate a result that is fixed, then we can just eliminate those pieces of code and compute less. So that's the first step. After that, we take each operator and represent it in loop format and just iterate to optimize that pieces of compute. There are various techniques like tiling, vectorization, pipelining. Essentially what's happening there is making sure that we are arranging the computation in a way that will keep the accuracy and the intent of the developer of the model, but make it more performant and run more efficiently on top of the hardware. At the end of this phase, we take the inner loops and move them to the hardware intrinsic mapping, which is basically lowering them to language that the Trainium can run Trainium and Inferentia. And then the last step is scheduling and allocation. That's basically taking all the pieces of compute and ordering them in a way that can parallelize compute as much as possible, again, to increase efficiency. So now that you're compiler experts, I'm very, very happy to announce a new feature that is coming soon. We call NIKI, and that's Neuron Kernel Interfaces. Neuron Kernel Interfaces is allowing developers to write their own performant kernels on top of Trainium. It's basically a bare metal interface that allows you to develop whatever innovation you want, run it performantly on Trainium, and you can see it essentially bypasses almost all of the steps of the compiler and allows you to run bare metal natively on top of Trainium. The APIs to do that are the same APIs that OpenAI invented with Triton. So folks that are familiar with Triton from OpenAI will find this environment familiar. You can see an example of softmax, which is a popular part of a very popular operation in language models. And we actually used the NIKI to optimize softmax performance on top of Trainium. So we use that already internally, and this is coming soon with detailed documentation of the hardware to customers. So super exciting, and this will allow customers to basically invent new models on top of Trainium performantly. Let's go back to Hugging Face. When you use the Hugging Face with Trainium, this is a training example, you use Optimum Neuron. Optimum Neuron is a package that is basically a wrapper technology that we supply, and it automatically helps shard models. It can be used for training and for inference. Today we'll talk about inference, but similar principles apply for inference as well. Tensor parallelism is a way to shard the model shard the model layers across multiple accelerators. So you can see it graphically on the top. In order to achieve that with neuron distributed, all you need to do is import, of course, the needed bits, and then define TP size of 4, and that will shard the model into 4 different subsections that can run concurrently on different accelerators. Similarly, if you want to do pipeline, that's another technique of sharding. You can usually pipeline across servers, so you do that over the network. You can cut the model in the middle. You define PP size, pipeline parallelism, PP size of 2, and load the model, and it will run. This is again the same Hugging Face Llama 7B model. So now that you guys know how to do this, you can see that in order to run the full training, TP size defined of 8, and then there are some hyperparameters that additional hyperparameters that you can control and define, and simply create the Hugging Face trainer instance and start training. Once you start training, you get a set of utilities like Neuron Top, which is like Linux Top. Basically, it gives you visualization of the utilization of the neuron cores, memory utilization of the neuron cores, and of course the host. You can you get all of that also logged, so you can trace it over time. But it's a very powerful tool to understand how effectively you are utilizing the hardware. And similarly, there's also native integration into things like TensorBoard, that you can track the curves of your training and make sure that everything is progressing according to plan. Last update I want to give you guys is very exciting as well in training. When we launched Trainium, we were building ultra clusters. Ultra cluster is the non-blocking petabit networking technology within AWS to allow all of these massive clusters of chips to work concurrently. When we launched, our maximum ultra cluster size was 30,000 chips. I'm now happy to announce that we're already building 60,000 chips, Trainium chips, in the data center. So that will allow even running larger models and, of course, finish training faster. With that, let's hear how Databricks are using Trainium. Navin? Thank you.
As a former hardware engineer myself, it was a little, it was cool to see the early days, but a little cringeworthy when you saw the servers on the carpet. That's like a big no-no, right? Anyway, yeah, so my name is Navin Rao. I was a previous CEO and co-founder of a company called Mosaic ML, which was recently acquired by Databricks to essentially run and build the generative AI strategy at Databricks. If you're not familiar with Databricks, it's a data platform for organizing data across many different tools, building pipelines like ETL and business analytics, things like this. And generative AI has now come on the scene as, I think, the way to express the value of that data. And so it was a very natural partnership for us. In fact, we had multiple customers that we were working with together using Databricks and Mosaic to build models. And it just became really clear that it made sense to join forces. So what do we care about? Like, we are building models ourselves, and we're using those as sort of a base for our customers to then go and customize from. So cost, performance, scale, all the things that Gadi was talking about actually become quite important to us. We have we have about 10,000 customers. Can you hear me? Okay, it's kind of going in and out. 10,000 customers, 6,000 employees, $1.5 billion in revenue. We're growing very fast, and I think this whole idea of organizing enterprise companies' data and then providing tools on top of it is actually really starting to gain a lot of maturity. I think this is going to be something that's as big as cloud in the next 10 years or so. So when we start talking about things at this scale, you inevitably have to start talking about cost, and you have to start talking about optimizing that through software and great engineering. And so that's why we're pretty excited to be here with the Trainium team and actually, be part of that journey with them, partnering early. It's a small team, and I think they're hungry to make something that's really great. So I'm hoping we can achieve that together. So as I mentioned, the data lakehouse was this pattern that we established as a company, Databricks established as a company, to unify all organization systems of data and some visualization on top of it. So now adding generative AI on top of this as a natural extension equals what we call a data intelligence platform. Really, generative AI is a way to take data and make it interactive. I can now ask questions of it. I can reason over things that are relevant to that data. I can build better tools like entity extraction, removing PII. These kind of simple things actually work really well. These sound somewhat boring, but in enterprise context, this is a very hard problem to do well, and actually can have massive operational savings for a lot of companies out there. And that's what we do as a company. So our platform roughly looks like this. We have what we call a Delta Lake, which is where you essentially dump all your data. Things can be in S3 buckets, they can be structured, unstructured, all kinds of different forms of data. And we apply a governance framework called Unity Catalog. This allows us to trace the lineage of data, where it came from, when it was imported, who imported it, maybe some permissions around it, and essentially start applying access control to that data. So certain users can see certain types of data based on those attributes. When we start talking about generative AI models, again, as I mentioned, it's an expression of data. We want to apply that governance model to those models as well. So let's say I take an open source model like Llama 70B, and I fine-tune it with some sensitive data for a sensitive application. I actually want that fine-tuned model to inherit those attributes of the data, because now that model can actually potentially regurgitate some of those facts. That might be a feature, it might be something I want, but I don't want all my users to be able to see it. So I need to inherit those attributes, access control to that model. And so this is what our platform does, is actually create all of these tracing and auditability mechanisms. So if you're in a regulated industry, say, you need to understand this user hit this API, got this output at this time on this model that was built on that data. And so I think all of this audit log needs to be tracked somewhere in an organized fashion. That's a lot of what we do. The intelligence engine is actually a new thing we're bringing out. We actually just demoed it at a competitor's cloud, we'll say, just recently, where we can actually start typing queries in English. So what we're trying to do now is expand this whole platform with generative AI, the data intelligence platform, as we have this set of tools like SQL engines and things like that you can build very structured queries to find specific kinds of information or specific kinds of dashboards and things on your data. But we also want to extend that to users who are not experts, who can't code in SQL. And so actually being able to query things in English, saying, what were my sales in EMEA for the last 10 years for this product, right? That might be something an analyst would ask. Right now, that person has to go and get someone who can code that up into SQL. That SQL person needs to understand how the databases are structured, what joins and this and that have to be done. We want to collapse that all into just making it an English query. And so I think that's really where we're going over the next several years. So it's a very exciting time, really, when you start thinking about data. The last 20 years in tech, we've been talking about data, logging it, but we couldn't really do anything with it. Now we're getting to the point where we have the tools to do that, and I think generative AI is a big unlock there. So because of this unlock and the tools like we're bringing to the market, we actually see that it is changing the future of work. We're seeing humans becoming more efficient. Now I know there's a lot of a narrative out there about doom and this and that, but I think really I see it as a way to make each human more efficient. I don't see it as a replacement. I see it as one human who does a certain task, like an accountant or lawyer, can do that task more efficiently. They can have essentially higher throughput. So that reduces costs, allows those humans to do other things that might be of higher priority. So I think I really see it as this assistant pattern over and over again. And so there are numbers here that from some surveys that we've conducted, like 75% of CEOs are now looking at generative AI as a competitive advantage. And really, most of them are thinking about this operational side of it, but it's going to start hitting their products soon. I think that's pretty exciting, where we can start interacting with computers in naturalistic ways. This is something I think tech geeks like me have dreamt about my whole life. So it's really, really great to see it. And we're seeing this across different verticals, and I'm sure everyone here has seen these verticals out there, but financial services, healthcare are really the areas where we're seeing a lot of uptake first. That's, of course, beyond the tech world. The tech world has embraced and used technology the fastest. We're now starting to see media, creating new images and video from large-scale AI models is something that has only been possible for the last maybe year or several months. And so now that stuff is getting really good. You can do very rich video. I'm seeing new companies launch all the time with this. We'll hear from one in just a moment here. But yeah, I think the future of media is actually kind of being shifted. The ability to rapidly prototype is changing. So we're seeing actually some uptake there. Some of our customers are now starting to build these sorts of things. Of course, manufacturing and government will be a long tail over the next 10 years. So why do companies come to us to build models? Well, using closed models like OpenAI, Anthropic, there's lots of use cases for them, but they don't cover every use case. There are many times where you need control over the model, meaning you need to understand what data went into it, you need to understand where it's being served, control its outputs very precisely. Like especially if you're in a regulated industry, you can't have something that you don't understand what data went into it. We see these little prompt injection attacks happen all the time now. It's fine for consumer stuff, but if I'm running something that's like, being trusted with legal documents or tax or finance, you really can't do that. So that amount of control is actually quite important. Getting things to be very good in domain requires domain-specific tuning. And that's actually a lot of what we do is, can we make an existing model better based upon the specific data and observations that our customers have? And then, of course, lower cost. Everything at the end of the day will come down to cost. It just always does. And as these solutions become more ubiquitous, the scale goes up, and then cost starts becoming the most important factor. So I think it's a really important thing to think about that scale up front. If you have an understanding of where a solution is going to go in a year, it can give you a lot of hints on how you should attack the problem. Maybe I don't want to invest in just an API. Maybe I actually do want to start thinking about using tools like Databricks Mosaic on AWS to customize models, because then you can really control the costs. And actually, this is something we did from the very beginning. So Mosaic started in 2021, which seems like ancient times at this point. But we wanted to apply algorithmic methods to reduce costs. In essence, every computing flop, like Gadi was talking about, these matrix multiplications are just floating point operations. Every one of them is precious. Each one of them costs money. No matter how many billions you have, there's a physical piece of silicon running that uses energy, and it's taking up floor space. So all of that costs money. Can I make each one of those flops more effective in learning from data? That was the question we asked. And so we actually have done a lot on this and reduced the cost dramatically on certain things. This is actually training stable diffusion. We actually have our own diffusion model. It was something on the order of 600K back in the end of last year, and we brought that under 50K. I think it's actually closer to like 30K to train a model from scratch. So something that's 30K is actually quite accessible. And we're seeing similar drops in LLMs. So GPT-3 sized models. We published a blog last year. It was about $450,000 to train on A100 GPUs. With things like Trainium, we're going to bring that cost dramatically down. This is going to be something on the order of below $100,000. Actually, we have a whole new set of innovations on this, and also using lower precision. We've already brought it internally much below $100,000. So that makes these things super accessible. Many enterprises can build, and customize these models for their use cases. And so, this is actually a fun case study we had here. The Texas Rangers, the baseball team, is one of our customers. And they actually use Databricks and the ML capabilities to do analytics on their players, like actually, swing motions of batters and pitchers and things like this. And it's a funny story, because it's almost like hard to believe, but they literally went from like a middling team. They used Databricks, and now they won the World Series. I don't know if we can claim credit for it or not, but it is actually kind of a cool story. And what's funny is a lot of other Major League Baseball teams are now signing up. So I think we're seeing data analytics, ML, and Gen AI kind of coming together to solve all kinds of interesting problems. This is just a fun one that we all can kind of sink our teeth into a little bit. Okay, so getting to the technical stuff a little bit. What we built at Mosaic is a platform that's actually multi-cloud. I know if I can say that in an AWS conference, but multi-cloud and also multi-hardware. And really the idea is that we can bring the price down by giving more flexibility to the user across different hardware and even different clouds, and make the performance higher. So can we deliver more, faster, and cheaper? And that's why we're really keen to work with the Trainium team, because they're focused on that specifically. And I think this is a key tenet of AWS, is deliver more for less constantly. And that's exactly what we're trying to do and enable this for users. So, Gotti went through the software stack. That's hard to use still, right? And it's not a bad thing. It's just it's a deeply technical software stack. It's not something that a general user of PyTorch could probably go and optimize on their own. And so that's where we come in, is we package these things, we make them work at scale, we deal with node failures and all these kinds of things that essentially abstract away the details of running the infrastructure. And we make it super easy for our customers to go between GPUs and Trainium or whatever. And so we have some critical components here like Composer and LLM Foundry. These are open source tools. You can actually go play with them yourself. This is actually the basis of our stack. There's a lot of other parts of the managed stack, of course. But we support inference, fine-tuning, pre-training. There's many different types of fine-tuning as well. And of course, now we're adding training support. And I think Gotti touched on this as well, interesting forms of parallelism. As I mentioned, I actually have a hardware background as well, so I love this stuff. New kinds of parallelism are very interesting to any hardware geek and actually linear algebra geek. But really what it comes down to in the end is that I can build bigger models and make them go faster and utilize that hardware more effectively. These kind of novel interconnects actually allow me to use more flops per chip. So just a quick primer on the economics here, like the chip is a fixed thing. I get it, it's a physical device. I want to extract everything out of that chip. And the only way I can do that is when I'm distributing that workload, I need to make sure that I have enough communication bandwidth in the right sort of configuration to be able to extract all of that, all those flops. And so really, these 3D parallelisms make a big difference here. And so the team is now adding support for the MPT models. These are our foundation models, Mosaic pre-trained transformers. We'll have a new set of models coming out very soon that hopefully we'll be partnering more deeply with the Trainium team on. And Llama 2, of course, we support as well as Mistral. So looking ahead, we're working on bigger and bigger cluster sizes along with the Trainium team, and hoping to see that great performance that we can pass on in terms of cost and speed to our customers. So thank you for your attention.
Hey everyone, my name is Pete. Really excited to be here to tell you a bit about Leonardo and how we use Inferentia. So Leonardo is a generative AI company focused on generative visual assets. That's things like images, video, and textures for 3D models. We launched about 12 months ago. We have millions of users. We have hundreds of thousands of community models trained on our platform. And every day, our service is used to generate millions of images, or millions of users even. So for those of you new to the space, the simplest form is called text to image. You supply a text prompt, for example, a cool dog, and you get your image back. On our platform, we have specialized models and methods that make it easy for anyone to generate stunning images. One of our newest is called Photoreal, which excels at generating photorealistic images. Another pipeline we have is called Alchemy, recently updated to support SDXL. These are some images generated with Inf2. They're enhanced with our proprietary Alchemy Refiner model, which takes an image as input and works great for a variety of styles. So at Leonardo, we were experiencing explosive growth. Demand for our service just kind of really took off. We ran up against the industry-wide capacity constraints for our accelerator hardware. And we had an existing platform built on AWS, so things like our CDN, object storage, and database were already on the AWS ecosystem. Given our situation with the capacity constraints, we started to look around and found Inferentia. Had a very appealing price-performance profile. I think GenAI is so new, it's important to keep an open mind to new developments and take the time to investigate how they may help. Finally, AWS has a really strong commitment to innovation. We can see the support for Inferentia across all of the core services we were looking to use. So I'll talk a bit about inference workloads at Leonardo. I'd like to compare them to training workloads because I think that's where a lot of the conversations are these days. And so in training, you have one model that you want to run on all of your hardware. You'll do a round trip through your entire data set, potentially many times, and jobs run for a very long time, days, weeks, maybe even months. And that's not what inference looks like at Leonardo. So we have many different job types, not just text to image. We have a very short job time, so typically 5 to 10 seconds. We change model every job, so we have over 400,000 models on our platform, and each job could use any of those models. We have a very clear peak and trough in demand throughout the course of the day, so ideally we'd be able to scale out and scale back in again, but that's not possible given the capacity constraints. And we have a few very popular models, so many of the images generated on our platform use a very small subset of models. And so if you think about if our data set is all the model artifacts on our platform, we typically only touch a very small percentage of those, and those popular models are the one we decided to target for Inferentia. So what did our path to adoption look like? So from the outset, we had two clear non-negotiables, image quality and generation time. So image quality had to be equivalent to what we were already getting, and we weren't going to ask our users to wait any longer to get their images back. So firstly, we got up and running on Inf2. We got familiar with Neuron, worked through the examples and understood the process. We then validated that the image quality was there and what we needed, however generation times weren't where they needed to be. We went through a few cycles of iteration, incremental improvements, and finally the generation times got to where they needed to be. We did some architectural integration and then deployed it to our platform and into production. So what did that architectural integration look like? Jobs enter our service via an SQS queue. They're picked up by a job routing service running in ECS. The job router inspects the request to see if it can be served by Inferentia, and if so, it sends it to a real-time inference endpoint running on AWS SageMaker. If not, it goes to our existing inference service. And then finally, the generated images are written to S3 and made available to the user. This slide shows our realized price performance benefit for a latent diffusion model running on Inf2. Image generation runs around 96 to 97% of the speed of our existing fleet, and given the short job times, this is essentially unnoticeable from the user perspective. The cost to process a job is 80% lower on Inf2 instances, so we get the same image quality, effectively the same job time, and around 20% of the costs. And this completely changes the value proposition we can offer, letting us give our best features to our users at a more accessible price point. So what's next for Leonardo? We're going to get all of our popular models up running on Inf2, including SCXL. We're experimenting with data parallel, so sharding the batches over several accelerators will further reduce generation times. Digging deeper into compatibility with more advanced features such as our proprietary methods. We'll transition from SageMaker to ECS and EC2. I really love SageMaker. I think it's a great platform. EC2 just better aligns with our existing setup for automation, observability, and analytics. We're already running other types of models, particularly language models. I think once you're up and running, it's very easy to get additional models up and running. And as we grow, there's more and more places for us to adopt AI under the hood. And Inf2 kind of alleviates the concerns around cost and capacity. And finally, it improves accessibility to the technology, what is a really transformative technology. So my top 3 tips, if you're looking to get started, just pick a simple use case. Language models are great. There's lots of examples. Use SageMaker to get up and running really quickly, do your integration work, deploy and run. And if all of that sounds like too much work, sign up to Leonardo, make some images for yourself. So I hope that was helpful. With that, I will hand back to Gadi. Thank you.
That was awesome. Thank you, Naveen. Thank you, Pete. These were just 2 examples of what customers can do with our technology. Super excited to have these amazing customers. Let's take a quick peek on what's next. Adam in the keynote already spilled the beans, so I'm not announcing anything new. But here is Trainium 2. On the left side is Trainium, the one that we just dived into. And this is the Trainium 2 chip. If you guys remember, when I left the stage, I talked about 60,000 Trainiums under a single ultra cluster. We are building a 100,000 chip cluster with Trainium 2, and that each Trainium 2 is 4x the performance of Trainium 1. So it's like 400,000 Trainium 1s. And in terms of exaflops, it's 65 exaflops, which is roughly 30 times the fastest supercomputer that is existing today. It's just mind-boggling the amount of compute that will be on demand in the hands of customers that are building GenAI technology. We can't wait to get Trainium 2 up and running. It's coming next year, and I hope many of you will get started on Trainium 1. It's the same Neuron SDK for Trainium 2, and you guys will be set up for an amazing journey together with us. So with that, this is the end of our session. If you want to learn more, I covered the Hugging Face Optimum Neuron. This is on the left, and then a quick getting started guide on Neuron on the right. And of course, if anyone has any questions, happy to address them now for me or for Naveen or for Pete. Okay, I guess everything was clear, so that's good. Really appreciate the time, folks. If you have any private questions, we'll be here. Happy to get a few more questions in the time we have left. Thank you.